Thank you very much, and thanks to everyone for being here. Today, my colleague Netesh and I will present you a causal inference framework that we have applied to estimate the impact of app installs. So this is our team, and Netesh and I are both data scientists, and we will take you through this talk where we will give you high-level kind of guidelines on using causal inference with observational data. So let me tell you a bit about how this talk will progress. First, I'll introduce our case that we have used this approach, and then I'll talk about our quasi-experimental setup. Then Netesh will talk about other approaches that we have considered or applied, and also he will take you through assessing the robustness of the estimates. And before I continue, I want to ask, how many of you have a Booking.com mobile app on your phone? Okay, very good, very good. I hope you are happy customers. And our talk will kind of relate, at least the case will relate to our app. Specifically, we'll talk about the installs. As you know, we have seen many of you have the app, and you have probably installed this in different ways. Some of you have searched this on App Store, for example, and if you have clicked on one of the organic search results, that's totally a free install for us. We are happy that you are using the app, and we have not spent any money on this. But there are also a lot of ways that we kind of advertise the app. For example, the sponsored search results or on Facebook, etc., so that people can find the app more easily. But obviously, we invest money in there. So the question is, how much should we invest in app marketing campaigns, and where should we invest? And to kind of have a strategy around this, we need to know how valuable app installs are and how much incremental value that we get through these installs for our customers. For that, we need to have a way to measure the impact of app installs. Ideally, in an ideal world, we will just kind of have a sample and randomly assign some of you to install the app and some of you to not install the app. But obviously, in real life, we can't force anyone to install. Instead, everyone's self-selecting to installing or not installing. So we have to rely on observational causal inference to make any causal claims in that area. But of course, this doesn't come for free, and it comes with its own challenges when we go the non-experimental route. And the main challenge here, this is like a simple, very simplified causal diagram. And the main issue here that if we were to naively try to install, we try to measure the impact of installs on customer lifetime value, we will probably get spurious inflated results because usually people who are high-value customers for us, they are way more likely to install the app, and also they are more likely to have very high customer lifetime value. So we need to be very careful, and we need to have like a approach to kind of get rid of all those unwanted customer attributes that might result in biased results. For that, our main, the logic is we want to find similar customers, but some of them, like in the first timeline, they have installed the app, and the others have not installed the app. And the idea is to find, after finding these similar customers, to compare their, let's say, the 1-year booking value to those who did not install the app. And that would give us an idea, a measure of how valuable the app install is. So that's the main thing that we want to achieve throughout this talk, actually. So now that we have understood the problem and how we will approach, let's talk in a bit more detail. So under this, if we want to find similar customers and we want to make a unbiased estimate, we have to rely on a couple of assumptions that are super important. The first one is unconfoundedness. And this means that once we condition our analysis on customer attributes, like for example, how recently they have booked with us or how valuable their booking was before installing, the install should be as good as random. So it should not be driven by any other factor that might result in biased estimates. Unfortunately, this is not testable, and it's a very strong assumption. But there are ways to quantify the risk of confoundedness, which Netesh will talk about in the second half. And the other two important assumptions are first, overlap. This means that we need to have customers who are similar enough, but some of them installed the app and some of them did not, so that we can make apple-to-apple comparisons. The other assumption that I won't get too much into detail means that we need to have, like, the treatment should not interfere with the outcomes of another unit that is not treated. So next up, once we have talked, we know the assumptions. First step is to kind of carefully think about which variables you should consider to include in your analysis. There are some, I will give you some very high-level guidelines. The first one, as we talked, we want to not have any confounders left out. So we want to include confounders. These are variables that affect both the treatment and the outcome. This is, like, I think, the most crucial point. The other thing is to incorporate any variables that affect the outcome, because that will improve the precision of the estimates. The other thing relates to, again, unconfoundedness, is sensitivity analysis. I think this can be important if you want to quantify the risk of confoundedness, which Netesh will talk about. And the other few things that I'll just very superficially go over because of time is to include only pre-treatment variables and not include any post-treatment, because that would bias your results. Also, there are other things that you might have come across, like M bias. This is a sort of collider bias if like two other variables are related to some variable, and if you include this, you might end up with bias again. So this is also something to consider, but we have a blog post about this, which we will link. It is quite complex, and you can read more on this if you want. So we want to, like, as I said, we want to find similar customers, and we have kind of considered which covariates to select. Now it's time to see how we condition on the covariates that we have selected. So to make things easier for us, we use propensity scores. Propensity scores are just they simplify or summarize different customer attributes into a single number. And for example, and this propensity score means how likely a customer is to install. For example, if they have recently booked with us, or they have made a high value booking, they are more likely to install, and we can just kind of understand that through the propensity score. And the idea is that customers with similar propensity scores will have very similar attributes. And we can actually check that with covariate balance plots. In this case, we have plotted the standardized mean difference, so how big of a difference between the two groups, treatment and control. So the blue dots show before we condition on propensity scores. As you can see, they are very spread out. That means before we condition or match on propensity scores, we had the customers who have installed the app versus not. They were very different. But after we condition on the propensity scores, the differences are minimal. So that kind of mimics randomization as much as possible, even though we don't have an experimental setup. The other thing to check is that we want propensity scores that actually reflect the reality, in the sense that customers with higher propensities should usually install the app. So in this case, what we can do is to plot the mean predicted probability for customers and compare that with the actual fraction of treated customers. And we want to kind of these to go in the same, almost the same. So it will be like 45-degree line. And in this case, we are pretty close. So that means that propensity scores actually reflect the reality. And this helps with the estimation. And the last thing that I will talk about is the overlap, which is really important because that means that we have similar enough customers so that we can make apples-to-apples comparison. So in this plot, what I have is the blue shaded area is the propensity density for customers who have installed. And the orange is the ones who did not install. And the green area is where we have the common area. So we have customers who are similar enough, but some of them install and some of them not, so that we can make a reasonable comparison and get a reasonable estimate. And one thing to know is that if you have poor overlap, that would mean your estimates may not be very reliable, and it will probably limit your generalizability, meaning that you will be only able to comment on a very specific set of customers, which is not something we want. But those were all the things that we have checked, and now Netesh will take you over other approaches.
Thanks, Naz. So I'll quickly jump into the different approaches. The first one is the most simplest one, in nearest neighbor matching. We pair each treated unit with one or more control units using propensity scores to create matched groups with similar covariate distribution, thereby reducing selection bias and allowing for unbiased estimation of treatment effects. The strength of this approach is that it's easy and intuitive to implement with flexible matching options of one-to-one or one-to-many, and can utilize caliper constraints and replacement to optimize matching quality. This approach is useful when the estimate of interest is average treatment effect on the treated, because control units are matched to treated units, discarding unmatched controls. The limitations of this approach is that matching quality is heavily dependent on accurate estimation of propensity scores. Therefore, misspecification of the propensity score models, such as omitted variable bias or incorrect functional form, would result in poor matching quality if true relationships aren't captured. Moreover, matching quality is also heavily influenced by hyperparameter choices, such as distance matrix, caliper settings, and replacement choices. And poor hyperparameter choice would result in biased estimates. Sparse data can also result in poor matching quality, especially for regions with lower overlap, as nearest neighbor matching can enforce a bad match if treated units lack close control. And lastly, this approach is inefficient in balancing accuracy and power, because we discard unmatched control units, which results in lower power and higher variance. We can address higher variance by using one-to-many mapping, but in that case, the estimates would be biased. The second approach is regression with propensity score adjustment. This approach is broadly divided into two stages. In the first stage, we estimate each unit's probability of taking the treatment using observed covariates. And in the second stage, we use the propensity scores from the first stage along with other covariates in a regression to predict the outcome. This approach helps control for measured confounding and allows for estimation of treatment effects, assuming no unmeasured confounding and sufficient overlap between treated and control groups. The benefits of this approach is that it's simple and easy to implement in standard regression frameworks and can be used in situations where outcome events are rare. Another benefit of this is that it can balance many confounders, because, as Naz mentioned, propensity score can summarize multiple measured confounders into a single variable. The biggest benefit of this approach is the double adjustment in the second stage, where we use propensity scores along with all the covariates to predict the outcome in a regression model. Because if there is any residual confounding from the propensity score model due to imperfect covariant balance, it's handled in the second stage. The limitation of this approach is that it's sensitive to model misspecification. So if the treatment or outcome models are misspecified, such as incorrect functional forms or failure to consider interactions, then this approach would result in biased estimates. Okay. The next approach is inverse propensity weighting estimator. In this approach, each unit is reweighed using inverse of their treatment assignment probability to create a pseudo population balanced on covariates. Here, treated units which look more like control and control units which look more like treated are given higher weights, thereby allowing us to estimate treatment effects. The biggest benefit of this approach is that it considers all available data. So this is more efficient than nearest neighbor matching. And the second is that this approach is consistent because we reweigh each unit by the inverse of its treatment assignment probability, which recreates the population distribution as if the treatment was randomized, which means that the average weighted average outcomes across treated and control groups would converge to true average potential outcomes as the sample size grows. However, this approach is highly sensitive to the misspecification of propensity score model and extreme propensity scores, as propensity scores near 0 and 1 could lead to extreme weights and variance inflation in the estimates. Doubly robust estimators, it combines outcome regression with propensity score weighing. So it adjusts for confounding using both the treatment and the outcome model. This approach is doubly robust because even if one of the treatment or outcome model is misspecified, we can get valid and consistent estimates. Therefore, this provides an extra layer of safeguard against model misspecification, and this is the biggest strength of this approach. However, this approach is no better than any other approach if both the models are misspecified, and the variance of the doubly robust estimator is often higher than outcome regression alone. Therefore, this approach is more useful when we have enough sample size to effectively control for variance. The last is the most advanced one, which is the double machine learning. Here, the approach can be divided into 3 steps, where we use machine learning models to first predict treatment. Then we use covariates to predict the outcome. And in the third step, we use the treatment and outcome predictions to estimate the causal effects. This approach utilizes orthogonalization and sample splitting to recover unbiased treatment effects. The biggest benefit of this approach is that it can handle high-dimensional data and can handle complex non-linear relationships without imposing strict functional form assumptions. And most of the estimators within double-ML are also doubly robust, so it provides an extra safeguard against model misspecification. And it avoids overfitting because the models are trained on separate folds. Therefore, it improves generalizability. The limitation of this approach is that it's highly compute intensive, and it requires large data to give stable and valid estimates with lower variance. And the last approach that we'll talk about is different than all the previous 5 approaches. It's a design-based approach. The instrumental variable approach helps us estimate causal effects by using a variable or an instrument which affects the treatment but has no direct effect on the outcome except through the treatment. This helps us address confounding and endogeneity when treatment is correlated with unobserved factors affecting the outcome. We leveraged Get the App experiments at Booking, where Get the App banners are shown to users on MDOT. And so Get the App banners exposure is the instrument variable, installing the app is the treatment variable, and subsequent accommodation bookings is the outcome. Using a 2-stage regression, we first predict the treatment using instrument, and then in the second stage, we use the predicted treatment to get the causal effects. What we get from this approach is a local average treatment effect, which is the treatment effect for a subset of population who were influenced by the treatment. The strength of this approach is that IV helps us establish causality even with observational data, as it addresses confounding and endogeneity when treatment is correlated with unobserved factors. IV is also helpful because it can help approximate experimental setting by isolating the variation in the treatment due to the instrument. The limitation of this approach is that it limits generalizability because we only get an estimate for a subset of population. Another limitation is that it's really difficult to find a valid and a strong instrument which affects the treatment and has no effect on the outcome. And lastly, violations of exclusion restriction assumptions or instrument validity can have a significant impact on the final results, and these assumptions are not testable in practice. So we tried multiple approaches in our use case, and we encourage users to compare estimates across statistical and design-based approaches, because statistical approaches have modeling assumptions about treatment and outcome, whereas IV approaches use exogenous variation in the treatment to establish causality. By comparing estimates across these diverse approaches, we first reduce the risk of false claims by relying on a single approach. It helps us identify and mitigate biases such as unmeasured confounding and model misspecification, because both these approaches are sensitive to either model misspecification or unmeasured confounding. And lastly, it helps us strengthen causal evidence by triangulation of evidence. The challenge here is that the statistical-based approaches gives us the average treatment effect on the treated, whereas the design-based approach gives us the local average effect, local average treatment effect. And for a fairer comparison, we need to transport the local average treatment effect to the ATT, which we have not yet done yet, but it's one of our next steps, which we'll be doing at booking. One of the most fundamental assumptions of observational causal inference is that there are no unmeasured confounders, as Nas talked about, and sensitivity analysis can help us validate this assumption to a certain extent, because sensitivity analysis quantifies how robust our causal estimates are to potential unmeasured confounding by measuring the strength of the unmeasured confounder needed to explain away the effect estimate. The three notable approaches are from Vander Valley and Ara. They provided the bias formulas, measuring the minimum confounding strength needed to undermine causal conclusions. Sinelli and Hazlitt, they expanded the omitted variable bias framework with partial R-square based sensitivity measures, which is only applicable for linear models. So this is one limitation. And the last one generalizes the sensitivity framework to nonlinear models using non-parametric versions of partial R-square. So depending upon the approach that you have used to estimate the causal effects, we need to select the appropriate approach for sensitivity analysis. We conducted sensitivity analysis at our end as well, and our findings were robust to higher degrees of unmeasured confounders. And lastly, following the principles that causality cannot be proven, it can only be refuted, we also leveraged multiple refutation tests, such as placebo treatment, where we replace the actual treatment with a placebo to observe whether if the causal effect goes to zero or not. Then in dummy outcome, we substitute actual outcome with an independent variable to validate if the effect goes to zero. Then in random common cause, we inject a random common cause to our inference framework to check if the estimates are still stable. In simulated outcome, we try to recover the true causal effect, which was defined as per a known data generating process. And lastly, in data subsample, we look at the stability of estimates across subsamples from the population. These tests help us check the robustness of our framework and our estimates, and helps build confidence in the causal findings. Overall, we want few takeaways for everyone to remember after the presentation. The first one is that we should have a careful covariate selection such that we do not omit relevant variables or condition on inappropriate ones, as it could introduce bias. The second is that we need to ensure that the treatment and control groups are balanced and there is sufficient overlap to have valid causal comparisons. Then try multiple approaches and compare statistical and design-based approaches to triangulate causal evidence, and implement sensitivity analysis to check the validity of unconfoundedness assumption. And lastly, run refutation tests to refute any false positive claims. Unfortunately, we cannot show the actual results from booking, and we have to mask a lot of variables as well. But feel free to reach out. We can give you general ideas about what problems we faced and our learnings in the entire process. Thank you.
Yeah, so we have 5 or 10 minutes for some questions. I see already one hand over there. I'm gonna.
Hello, I'm a postdoc in economics, and I was very happy and surprised to see to hear so many like causal inference terms in this session. And my question is that I understand that you cannot force your clients to install the app or not, like by randomization. But as we know that propensity score matches cannot by itself solve endogenous problems and give us causal inference results because they are like unobserved variables that because they are unobserved that we by nature we cannot like use propensity scores to put them into account and build balanced treatment and control groups. So you also tried to use IV, but I didn't follow what your IV truly is. So my question is, in your main analysis, you use propensity scores, but have you tried to randomize by intention to treat and doing causal inference by randomization or intention to treat? Even you cannot force them to install, but this can also give you the causal inference. Or compliers. Yeah.
Yes, so that is what the instrumental variable approach was about, where we randomized the traffic coming to our mobile website into treatment and base, and customers, users who went into treatment, they were exposed to get the app banners and encouraging them to install the app. So that was the instrument variable, which was randomized, and we use that approach to estimate the effects. The only thing is that we need to be careful that the exclusion restriction assumption is not violated, because we face this in the actual problem itself. Because if you show the banner in a pre-funnel stage and customer installs the app, it disrupts their booking flow on MDOT, which can have an impact on subsequent outcome or accommodation bookings, because customers can drop from the funnel. So therefore, we used banner experiments which were in the post-book phase. So after customers arrive on MDOT, they make a booking, then if we show them the banner, then we do not violate exclusion restriction assumptions, such that it only affects the treatment, that is the app install. And since the customer has completed their booking flow, it does not have a direct impact on the outcome.
Yeah, I wanted to add, like, we can do some limited, like, intention to treat tests, like this one for certain channels, but we can't do that we have many channels, like in some phones, like the app is already installed, for example. So that's one of the ways that we also, I guess, make people install, but there's no way to kind of do that incentivized designs in other channels. So it's not very scalable, but we use that for validation of our observational results as well. Hope that answers.
All right, we'll have time for one question more.
Thanks for the presentation. I have a question about the propensity scores overlapping slide, if you can go there. So if I see this, like the blue one are the treatment, the 0 is the control. I see overlap up to 70%, like 0.7. However, from 0.7 to 1, there's no overlap. And also, like with the title, that overlapping is very important and crucial. However, looking at that, gives the impression that probably you can't apply causal inference. So how do you approach this?
Exactly. So that's a good eye. You catch us there. But indeed, that's a very important point, that we do not have overlap, like, let's say, from up 0.8. And that means that we do not have good comparisons for the people who have installed there to the, with people who did not install. And the classic way to approach this is that to trim the propensity scores where you don't have the overlap, so that you don't make wrong comparisons or extrapolate where you don't have good comparison units, which is what we also do. But also one thing that I want to mention is that that also is a limitation of this approach, right? We can't generalize results to all propensity, all different populations, but that means that we are kind of limited with generalizability for certain, but still a very wide range of customers, I would say.
Yeah, it only changes the interpretation of the estimate. So usually this approach gives us average treatment effect on the treated. So as Naz mentioned, we restrict our focus on only the support area. So the estimate that we get is average treatment effect of the overlap region, and accordingly we use these estimates in the subsequent applications, such as bidding for app marketing campaigns. Does that answer?
We have one last question.
Something came to my mind just right now when we were talking about this overlap. Maybe the part that we don't have overlap is because of some variable or some factors that we can't even control. There are some population that would install anyway. So maybe that's the part that we need to consider when we were thinking about the first two populations that we selected and we wanted to have the maximum overlap. Because, for example, maybe there are certain level of education, age, I don't know, income, something that those people will always install, and we can't even find non-installers from that population.
It's a good question. The reason that I understand, like based on my understanding, is because we don't have covariates with respect to exposure to app marketing campaigns. So what we look at is internal booking data, like past customer behavior, how loyal they were, how many bookings they have made in the past. These are the covariates that we use to address selection bias. Selecting self-selection into treatment can be influenced by exposure to different campaigns, because we run campaigns across Google and Apple to encourage customers to install the app, and that data we don't have, like which users were exposed to. So so as you pointed out, like for like age, education, customer-related attributes we do consider, but exposure to app marketing campaigns, we don't have the data for it, so it's one of the limitations in terms of the observed covariates that we have.
All right, let's give a last round of applause to our speakers.